So this lecture, I'll go over some problems on multiple integrals. I've given you detailed solutions for 9 here, 17, 27, and 28. So I will do the other 5 in this lecture. The first problem is a double integral. We can see that this is going to be hard to integrate with respect to x, and it'll be hard to integrate with respect to y as well. So interchanging the order of integration isn't going to help much. So the other method we have sometimes for doing difficult integrals like this is to go ahead and convert to polar coordinates. And there's some hint of that by the fact that x squared plus y squared is r squared. So that'll make that simple. And that this is a region that looks like a circle. If we check this here, y is going from -3 to 3. For each fixed y, x goes from 0 to this circle of radius 3 centered at the origin. So where x is positive. So this is x squared plus y squared equals 9 if we rewrite that. And this will be, again, a half circle in the xy plane where we're to the right of the y-axis, and the circle has radius 3 centered at the origin. So in polar coordinates, we're going to want theta to go from where to where? Well, this is going to be easier if we go from minus pi halves to pi halves. We've been generally taking theta between 0 and 2 pi. You could break this up and do from 0 to pi halves, then from 3 pi over 2 to 2 pi. But it'll work to go ahead and go from minus pi halves to pi halves for theta. And then r goes from 0 to 3. That's the radius of the circle in the xy plane. And so that will give us the limits of integration for our double integral in polar coordinates. So again, theta from minus pi halves to pi halves. And then r is going to go from 0 to the radius of that circle, which is 3. And as I mentioned, the x squared plus y squared gets replaced with r squared. And then we have dx dy that has to be replaced with r dr d theta. So now we just want to do this double integral. And it looks like we want a u substitution there with u equal to 7 plus r squared. Then r dr will be 1/2 du because du here is going to be 2r dr. So we get r dr is then 1/2 du. And so we're going to replace this r dr with 1/2 du, and this will be u to the minus 1/2 here. So the square root of u in the denominator will be u to the minus 1/2. So the integral we're basically doing is 1/2 du coming from, again, the r dr. And then we have a u to the minus 1/2. So when I integrate this, I'm going to get u to the 1/2 over 1/2 times 1/2. So it's just going to be u to the 1/2 plus a constant here. So if u is 7 plus r squared, we're just ending up with 7 plus r squared to the 1/2 when we integrate what's inside here. So 7 plus r squared to the 1/2. And we're evaluating this from r equals 0 to 3. When I plug in 3, I'm going to have 16, 7 plus 9, to the 1/2, which is 4. And when I subtract 0, I'll have the square root of 7 I'm subtracting, so it'll be 4 minus the square root of 7. So this is 4 minus the square root of 7. And I can take that outside the integral, it's a constant. So I have 4 minus the square root of 7, and I'm now multiplying that by the integral from minus pi halves to pi halves d theta. So this is just theta evaluated from minus pi halves to pi halves, and that's just going to give us pi halves minus a negative pi halves, which is pi. So this is just going to be pi. And so I have 4 minus root 7 times pi. And that's the answer then to the value of this double integral. So that finishes this problem. Let's look at problem 12 now. This is a triple integral. We can see it's going to be a little hard to integrate with respect to any of the variables. So we do want to change the coordinate system. The x squared plus y squared plus z squared here suggests that maybe rho squared is the right thing to use here, because that will simplify. So probably spherical coordinates is right. Let's make sure that this is what it looks like. That is, it looks like a part of a sphere here. Let's check. In the xy plane, we have x going from 0 to 2, and y going from 0 to this circle of radius 2 centered at the origin. So it looks like in the xy plane, what we have is a quarter of a circle that's in the first quadrant, centered at the origin and of radius 2. So that's what this is describing. And since it's in the first quadrant only, theta is going from 0 to pi halves. And that's whether we're doing it in spherical coordinates or if we wanted to try cylindrical coordinates, theta is going from 0 to pi halves. So we have that for theta and that quarter of the circle. And now for the z part here, we have this is describing a sphere, because this will be the same thing as x squared plus y squared plus z squared equals 4. So we're on a sphere here and here of radius 2, centered at the origin. And since this is minus here and this is plus, we're going from the bottom part of the sphere to the top part of the sphere. So this is the bottom part of the sphere and going from there all the way up to the top part of the sphere. And we're inside this circle, this quarter of a circle here. So part of this picture here will be in the first octant, a sphere of radius 2 centered at the origin. And then right below the first octant in space, we'll also have that part of the sphere because we're going from minus this. So we have 1/4 of a sphere. It's a sphere that's in the first octant and right below that. And so it's going to be 1/4 of a sphere centered at the origin of radius 2. So for spherical coordinates, again, we have theta going from 0 to pi halves, like we discussed. Phi is going to go all the way from the positive z-axis to the negative z-axis because we have the sphere both on top in the first octant and then on the bottom below that in the octant below that first octant. So we're going to have it going from 0 up here in the positive z-axis to pi on the negative z-axis. Okay, so that's phi. And then rho is going to go from 0 to 2 because it's going from the origin to the sphere of radius 2. So we have 0 to pi halves for theta, 0 to pi for phi, and 0 to 2 for rho. Now let's check that we did the conversion correctly here. Z is rho cosine of phi. So that's why you have rho cosine of phi squared. Z was squared here. This again, x squared plus y squared plus z squared is rho squared. And when I take the square root, I'm going to have rho. And this is dv, dz, dy, dx. And that's going to be in spherical coordinates, rho squared sine phi, d rho, d phi, d theta. So this is our triple integral we need to evaluate. We can see we have a rho squared from here, a rho and a rho squared, so rho to the 5th, cosine squared phi and a sine phi. So let me rewrite that. So this is what we're integrating. We're integrating with respect to rho first. So we'll have rho to the 6 over 6. That's going to be 64 over 6 and then minus 0, but 64 over 6. And we can cancel a 2 to make that 32 over 3. So integrating with respect to rho is going to give me a 32 over 3. And then I'm just left with the integral from 0 to pi halves and 0 to pi sine phi cosine squared phi, because we already integrated that, d phi d theta. Now this integral with respect to phi, we have, if you do a u substitution here, u squared, u equal to cosine of phi. So we'll have u squared, du will be minus sine phi du. So this is minus u squared du if I do that substitution. Minus u squared du will be minus u cubed over 3. So minus cosine cubed over 3. Cosine of phi cubed over 3. We can put a 3 here, so that'll make that a 9. And so I have 32 over 9 now because I took that over 3 we were having and put it there. And we have the minus u cubed here. So minus cosine cubed phi. I want to plug in pi. I'm going to get -1 with a negative sign here, makes that a +1. Then I want to subtract what I get when I plug in 0. That'll be -1. So I want to subtract -1. That'll be +1. So when I evaluate a pi, I'm getting 1. And then when I subtract what's happening at 0, I'm getting another +1. So this will be 2. So I'll have 64 over 9. 64 over 9 times just the integral now of from 0 to pi halves of d theta. So that's just going to be theta evaluated from 0 to pi halves. That's just going to give me pi halves. Pi halves minus 0, pi halves. Now the pi halves, I can take the 2 in the denominator there and cancel with the 64 to get 32. So I'll have a 32 over 9 times pi. And that 32 over 9 times pi then is our answer for the value of this triple integral we started with at the top. Let's go to the next question. Number 14, we have a triple integral again. And we want to figure out what to do with this. Well, let me first comment that you don't have to do too much because you actually can integrate this with respect to z. This is a constant. You'll get z evaluated from 0 to y, so this will just give you y times x squared plus y squared to the 3 halves. And integrating with respect to y is not too bad. So if you just go ahead and try to integrate this in rectangular coordinates, it's not that bad. We're going to go ahead and maybe just for practice, convert this to cylindrical coordinates. So that's also a reasonable thing to do. This x squared plus y squared will be r squared, and to the 3 halves, we'll get r cubed there. We'll get another r from this because this is dv, which will be r dz dr d theta. So we get an r from here and an r cubed from here. So we'll have an r to the 4th in the end. We're integrating dz dr d theta, and let's look at the limits of integration. In the xy plane, we have x between -1 and 1, and y is going from 0 to this circle of radius 1 centered at the origin. So this is going to be a half circle above the x-axis, centered at the origin of radius 1. So theta is going to go from 0 to pi, at the top part of the circle, and r is going to go from 0 to 1 because the radius of the circle was 1. Now z is going from 0 to y. We have to convert that into polar coordinates also, and that's r sine theta. So the triple integral we end up with is theta going from 0 to pi, r going from 0 to 1, z going from 0 to y, which is r sine theta. And again, this got replaced with r cubed, and this got replaced with an extra r to give me r to the 4th, dz dr d theta. So this is the triple integral we're ending with. We just want to integrate this. With respect to z, this is a constant. So we're just going to have r to the 4th times z, where z is evaluated from 0 to r sine theta. That's just going to give me r to the 4th times r sine theta, which will be r to the 5th sine theta. So we evaluated the integral with respect to z. We got the r sine theta times the r to the 4th, and that's given me this. So next I want to integrate this with respect to r. That's going to be r to the 6 over 6. Evaluated from 0 to 1, we're going to get 1/6. So this is just going to be 1/6 then times the integral from 0 to pi of sine theta d theta. So this will be minus cosine of theta, evaluated from 0 to pi. And this is just like the previous problem. When I plug in pi, this is going to be -1. With this minus sign, we're going to get a +1 here. And then when we plug in 0, we're going to have minus a -1. And so that's going to be 1 plus 1, or 2. So this is giving me 2 times a 6. And so that'll be 1/3. And that then will be the value of this triple integral we started with is 1/3. So let me go to problem 20 now. But the x squared plus y squared throughout this problem suggests cylindrical coordinates. The picture, not very good for spherical coordinates. And in fact, what is this picture? We have a cone on the bottom, and you're inside a cylinder of radius 1 centered at the origin in the xy plane, so centered on the z-axis. So that means this circle at the top, the shadow of the solid, would be just coming from this circle, and it's a circle of radius 1 centered at the origin. It's just going to be this x squared plus y squared equal to 1 in the xy plane. So that's going to be the shadow of this object in the xy plane. So that's what we want to integrate with respect to in the xy plane. And again, that's just perfect for cylindrical coordinates. Theta is going from 0 to 2 pi around the circle, and r is going from 0 to 1 because it's a circle of radius 1. And z is going to go from the bottom here to the top. So it's going from this cone to z equals 4 here. This is the cone. This will be r. The square root of r squared will be r. So z is equal to 3r. So that's the cone. Z equals 3r, and this is z equals 4. So when we set it up, at least the limits of integration aren't too bad. Theta, again, is from 0 to 2 pi, going all the way around the circle. And r is going from 0 to 1. And then z is going from the cone, which is z equals 3r, to z equals 4, the plane. So that's the setup. Is that easier to integrate? Well, you realize once you integrate with respect to z, it is, because we're going to have z here, and it's going to be just 4 minus 3r when I evaluate z. So I'm going to have 4 minus 3r, and you have a 4 minus 3r in the denominator, so it's just going to be left with r to the 4th. So this is just going to be r to the 4th when I integrate with respect to z. I'm going to have z again evaluated from 3r to 4, so I'm going to get a 4 minus 3r times this, and the 4 minus 3r is going to cancel. And I'm just going to get an r to the 4th. To be fair, if I had integrated with respect to z up here and kept it in rectangular coordinates, the same thing would have happened. This denominator would have gone away, but you still would have x squared plus y squared to the 3/2 to integrate, which you could then do with polar coordinates. So we have this r to the 4th. We're going to evaluate the integral with respect to r there. So we're going to have r to the 5th over 5. Evaluated from 0 to 1, that's going to give me 1/5. And then I still have to integrate with respect to theta from 0 to 2 pi. So that just gives me a 2 pi times a 5th, so 2 pi over 5. And that then will be the value of this triple integral we started with that looked kind of messy, but in the end wasn't too bad. So that's the answer to that question. For the last problem, we have a triple integral again. It's given this time in cylindrical coordinates. A little hard to integrate in cylindrical coordinates. Looks like you might be able to do it with a trig substitution, but it doesn't look nice. So let's say we want to convert this to some other coordinate system. Rectangular coordinates, well, what would happen? R squared would be x squared plus y squared. This would be x squared plus y squared. You want to integrate this with respect to z, that's going to be messy. That's going to be messy all the way around trying to integrate with respect to x, y, or z. So probably we should use spherical coordinates. It's the only thing that's left. And why would that be good? Well, we just said this was x squared plus y squared, and then now we have plus z squared here. So this is just rho squared. Rho squared to the 1/2 will be rho. So this will just be rho. And what about the r squared? Well, before you do anything with the r squared, keep in mind that this is in cylindrical coordinates. So when I convert to spherical coordinates, I want to use that dv is r dz dr d theta in cylindrical coordinates, and rho squared sine theta rho d phi d theta in spherical coordinates. So I'm going to need this r dz dr d theta to rewrite like this. So I need to take one of these r's in this r squared and put it with dz dr d theta, so I can rewrite this as rho squared sine phi d rho d phi d theta. So we're going to take one of these r's, combine it with this to get this. Then you still have an r left. That r is rho sine phi. And again, this was rho squared to the 1/2 or rho. So that's going to be what we get when we convert all of this. Let's look at the picture here. Theta is from 0 to pi, and r is going from 0 to 2. So in the xy plane, described by the r and theta here, we're going to have the top part of a circle again, the half of a circle above the x-axis, because theta is going from 0 to pi. and it's a circle of radius 2, so it's centered at the origin. So we have a half of a circle centered at the origin of radius 2, and it's a half that's above the x-axis. And the sphere, this is a sphere, again, because this is x squared plus y squared, the r squared here. And so if I set these equal to z, it's just saying z squared plus r squared is 4, or z squared plus x squared plus y squared is 4. And that's going to be a circle of radius 2 centered at the origin. And this is the bottom part of it, and this is the top part of it. So we're below this circle in the xy plane, that's above the z-axis, this half circle. We're below that for our sphere, and we're above it. We're below it here and above it. So we're going to have half of a sphere. Okay, so the half that's cut off by the xz plane, and you're going to be to the right of the xz plane in space. So let me go ahead and write this in. Theta is going from 0 to pi because it was up here. That doesn't change. Again, we're going from the top of the sphere where we have the positive z-axis to the bottom where we have the negative z-axis. Phi is 0 at the top, and it's pi down here. So phi is going to go from 0 to pi. And rho is going from the origin to the sphere, and the sphere has radius 2. So rho is going from 0 to 2. Again, we only want one of these r's here. That's r sine phi. The other r dz dr d theta gets replaced with rho squared sine phi d rho d phi d theta. That's what's here. And this extra rho here is coming from this part, again, because this is rho squared to the 1/2, which is giving me rho. So this is the triple integral we want to evaluate in spherical coordinates. We're going to have rho and a rho and a rho squared, so that's rho to the 4th and a sine squared phi. Rho to the 4th, when I integrate, I'm going to have rho to the 5th over 5. Evaluate that from 0 to 2. The 2 to the 5th is 32. Of course, 0 to the 5th is 0. So we're going to have 32 over 5. So that part's going to give me 32 over 5. And then I'm left with integrating sine squared phi d phi on the inside here. And what about sine squared? Well, sine squared, remember, we replaced with 1 minus cosine of 2 phi over 2. Well, let me just comment. So we're going to do this as two integrals. We're going to integrate the 1/2. We're going to integrate this. But what happens when we integrate this? Notice the integral of cosine of 2 phi is going to give me sine of 2 phi over 2 by itself. But sine of 2 phi, when we evaluate it at 0 and pi, is just 0. Sine of 2 pi is 0, and the sine of 0 is 0. So when I evaluate this integral minus cosine of 2 phi over 2, I'm just going to get 0. Because you're going to end up with sine of 2 phi times something where the sine of 2 phi is going to be 0 at 0 and pi. So I'm really just interested in the 1/2 part here. When I integrate 1/2, I'm going to get 1/2 phi evaluated from 0 to pi. So we have 1/2 phi evaluated from 0 to pi. That's 1/2 pi. So I'm going to get pi halves for this inside integral. Again, the pi halves is coming from integrating the 1/2, and we get 0 when we integrate this. So we get 32 over 5 times pi halves times what's left is the integral from 0 to pi d theta. This is going to just give us theta evaluated from 0 to pi, which is just pi. So we get a pi from here. We can replace the 13 over 2 with 16. So we get 16 times pi squared, because we have 2 pi's here, divided by 5. So this triple integral and cylindrical coordinates that we started with is the same thing as a spherical triple integral, and then we end up with 16 pi squared over 5 for our final answer. So that's the value of this triple integral, and that finishes this lecture.